Hey everybody, in this video we're going to differentiate exponential functions, things that look like this, y equals b to the x. The key with an exponential function is that the variable is in the exponent, not the base. Also remember that when we are dealing with exponential functions, that base always needs to be positive and we require that it not be equal to 1. Here's what they look like. When b is greater than 1, we get exponential growth. The function goes towards infinity very quickly. When b is between 0 and 1, we get exponential decay. The function decays very quickly towards 0. We want to be able to calculate slopes of tangent lines to these graphs. To start out, we're going to need to use the limit definition of the derivative. Don't worry, we'll get through this part very quickly. So there it is. The limit as h goes to 0, f of x plus h minus f of x over h. I apply that to the function b to the x, plug in x plus h and plug in x. Then I have an exponent law I can use. B to the x plus h is b to the x times b to the h. I see a common factor there of b to the x. Notice it doesn't have any h's, so I'm going to factor it out of the numerator and also factor it out of the limit. So look what we've got here. We've found that the derivative of b to the x is b to the x times just some constant. The limit as h goes to 0, b to the h minus 1 over h is just going to be some number. To say this in words, the derivative of any exponential function is proportional to the function itself. That constant of proportionality, limit h goes to 0, b to the h minus 1 over h, just turns out to be the derivative of that exponential function at 0. So it's actually got a physical interpretation. Here we can write that. Here I'm writing it very efficiently. Derivative of b to the x is f prime of 0, b to the x. So there's one particularly nice exponential function, just based on that equation right there. It's going to be the one for which f prime of 0 is 1. In that case, the derivative of b to the x will just be b to the x. So that particularly nice exponential function we're going to single out. We're going to call b by a new name. We're going to call it e, the exponential number or Euler constant. It's the one for which the limit as h goes to 0, e to the h minus 1 over h is equal to 1. The Euler constant is one of the fundamental constants of the universe. It comes up in myriad applications. It's irrational, like pi, and it's about equal to 2.72. The function y equals e to the x is the easiest thing in the world to differentiate. The derivative of e to the x is just e to the x. We can do products, quotients, and compositions in the usual way. Let's do a few examples. E to the cosine x. So this is a composition. We need the chain rule. We're going to differentiate the outside function first and multiply it by the derivative of the inside function here being cosine of x. So the derivative of the exponential function is just the exponential function itself, e to the cosine x. And I multiply that by the derivative of cosine, writing it slightly more politely, negative sine x times e to the cosine x. Derivative of tangent of e to the x. It's another composition, another chain rule. This time the outside function is tangent. The inside function is e to the x. So when I differentiate tangent, I'm going to get secant squared, keep the inside exactly the same, and then multiply by the derivative of the inside, e to the x. Overall, e to the x secant squared of e to the x. Let's do one more, slightly more complicated example. X squared e to the 3x over secant of e to the x. So here there's a quotient. I'm going to need a quotient rule. There's also a product there in the numerator, so I'm going to need a product rule there. And I see a couple of chain rules in my future. Secant of e to the x and e to the power 3x. So first let's apply the quotient rule. I do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now I need to carry out those two derivatives. So in the first case, the derivative of x squared e to the 3x, doing a product rule, 2x e to the 3x plus x squared times 3e to the 3x. In the second case, I have a chain rule. The derivative of secant of e to the x, I need to do the derivative of secant first, that's secant tangent. So the inside's e to the x, so I get secant of e to the x, tangent of e to the x, times the derivative of that inside function. The derivative of e to the x is e to the x. The denominator is exactly the same as before. This can be simplified very slightly to give us a final